Okay, so last unit is on thermodynamics. So thermo means heat, dynamics means motion of heat. Okay, so talking about thermal expansion. By the end of this lesson, you will be able to explain how things expand and contract, different changes in temperatures, and understand how water responds differently. So, quick little chemistry review. Water freezes and boils. Hopefully that's already in your brain. Correct answer is D. Everybody good with that? Fahrenheit. The dance between Celsius and Fahrenheit. You got those conversions. Okay. Which I'll give to you. But here's the deal. I think it's just a good, like everybody else in the world measures temperature in Celsius. We're the only oddballs that are like, yeah, Fahrenheit, why not? So to be able to carry on a conversation and know, like, when someone says, hey, it's 30 degrees Celsius outside, to you is like, man, that sounds freezing. Okay, here's a quick way to make this conversion. 9/5 is really close to 2. 10/5. Okay, and then I just round that to 30. Okay, so it's 30 degrees, double it, 60 plus 30, you're in the 90s-ish. You're around the 90. That's kind of hot. Like, at least you have an idea. Or if someone says, some international student that's at Purdue is like, a really popular question is like, how cold does it get here? And you're like, oh, -10. And they're like, that's not too bad. And they're from like Africa. And you're like, I don't think that really registered. So you take away 30, so -40, and then divide by 2. So you can say it's around -20 degrees Celsius, and they'll be like, whoa, that's really cold. Just trying to feel like this is good practical. Okay. Kelvin, 0 degrees Kelvin is when all motion stops. Molecules, absolute zero. So at 0 degrees Celsius, that's 273 degrees Kelvin. I'm assuming, regardless of who you had last year, that all this stuff has been covered.
I think so.
Such a sad. I think we can do this, yeah. Such a testimony. All right. So that was a quick chemistry review. So, considering this lesson is on expansion, probably not a zipper. So D is the correct answer. Okay. So we do a lot of things design-wise, engineering-wise, that needs to incorporate expansion and contraction stuff. Okay. So roads will have like these rubber plastic accordion type things for expansion and contraction. Some bridges actually have rollers underneath to like allow for expansion and contraction. Pipes have these like across the desert. These are oil pipes for going across the desert. The temperature change on a desert is pretty huge. Railroad tracks, they slice them. You can expand and contract. You have expansion joints and bricks and mortar type stuff. So concrete, these stripes things, what these are designed for is where the sidewalk's going to crack. If you ever like scored drywall, like put a cut, you don't have to cut all the way through. You just need to put a deep scratch through it, and then you can smack it, and it breaks on that. This is kind of like scoring concrete. It's going to break. Where is it going to break? You want to put it in here. It looks better. And there's equations for like how thick you're going to make it, how often you put those score marks. I need to put a picture of this, but telephone wires around the place. Have you guys seen like where they've like do these teardrop looking things on like telephone poles, like in the middle, kind of in the wires? Okay, this is allows for expansion and contraction so that in the summertime your wires don't look like this, and in the wintertime they look like this. In the summertime it just wraps up a little bit more, and in the wintertime it unravels some. So cool that. So if you don't take into account expansion and contraction, well then bad things happen. Okay. Yeah, so good thing to take account, be aware of. Bimetallic strip. The name itself tells us that we've got two different metals on one strip. Okay, so here I have a bimetallic strip. Okay, and one side is one type of metal, the other side is another type. If I heat this up, even if I go this way, so which side has a higher rate of thermal expansion? The outside or the inside? The outside has a higher rate of thermal expansion. Does that make sense? It's expanding more than the inside. Good to that. Yep. So one application of that is a thermostat, like an old school thermostat. So they had a bimetallic strip wound in a spring type thing, and as it expands or contracts, it can turn off and on your furnace or air conditioning, depending on if you're cooling or heating. Cool with that? Okay. So let's say you have a slab of metal and you heat it up. It's gonna expand. Okay. Let's say you have a slab of metal and you cut a hole out of it. As you heat this metal, well, the hole get bigger, smaller, or stay the same? Everybody have an idea? Okay. What I have is a ring and a ball. The ball does not fit in the ring. Okay. So I'm going to heat this up. Wait for it. This is gonna be revolutionary. You should get your cameras out for this one, kids. I know you're gonna have to wait. I'm gonna say that's good enough. And it now fits. Yeah, first hour I had to heat this back up again. So one application of that is thermocouple. I know it's a risky endeavor. So if they have like two pipes and you have this sleeve or like this cast that's made of metal, you can heat up that. It's called a coupling. Heat that up, it expands, and then you can slip the pipes in both ends and then let that cool, and that constriction binds those two together. Cool with that? Okay. So when I was in your shoes, should have put that on the video. Let's do that again. So the hole becomes bigger. When I was in your shoes, I thought the hole was going to become smaller, kind of like the Stay Puft Marshmallow Man, like expanding and it kind of closes in. That's what I thought until someone showed me this idea. So you have a block of metal, and we're going to subdivide that into 9 squares. Okay. As it expands, that expands. Like, yeah. But if you like pop a hole out of this, that hole is going to get bigger. That makes sense? Okay. Everybody good with A? Life hack for you. Okay. This one might be the most practical thing you learn in school today. Got a hair dryer or heat gun. and he's going to take a can of air, which is just, I think, just nitrogen gas, but it's like liquid nitrogen, where you spray it upside down, which not recommended, but it's super cold.
That's amazing. That's freaking
I can't believe it
amazing.
freaking worked.
Like, wow. That is amazing.
He is bamboozling.
Holy. Will it work on these little ones?
No, it only works on like a couple.
You got another one over there on the other side, a bigger one than that one.
Yeah, but it only works on
That
ones that
is truly amazing.
it only works on ones that you haven't creased.
Check that out, man.
Thank you.
You're welcome. And free.
Okay, so only works with metal cars. That's not going to work with fiberglass. I've never tried this, but according to this guy, it doesn't work if you've bent, like the metal has been creased. If that makes sense. It's just kind of a softer, smoother dent. So the idea is this. He did the hair dryer first to kind of, I'm going to say, not loosen the molecules, but like get them moving a little bit more and make the contrast of hot to cold more drastic. So if you are going from like point A to point B, here's the dent. That's a longer distance than here from point A to B. So like when it got cold, it contracted and shortened that distance. Does that make sense? So can of air, that's definitely, it's worth $5. Want to try to get a shot out? I told him to come back in here if they were not done. So Carter, you can come on back over here. Just have a seat at a table somewhere. Okay. So water is different. So when water freezes, it becomes less dense. This is not usual. Usually things constrict when they get colder, but water expands. Okay. So the reason for that is when water freezes, it becomes really organized and actually spreads out in this crystal lattice that's very spacious, I guess we could say. Okay. Versus in water. So this is what makes ice less dense than water. Okay. We've all experienced this idea that water expands when it freezes. Okay. Throwing a can of Coke in the freezer, water bottle. Okay. It gets really bad if you like rupture pipes in the winter time if your pipes freeze. Okay. You also breaks apart rocks even, like water gets in the cracks, freezes, expands, and okay. And this is what causes potholes. Okay? In the great state of Indiana, and during wintertime, it flips between freezing and non-freezing often. Okay, so water is going to get into the cracks, freezes, expands, pushes that apart, makes the cracks bigger, melts, drips down lower, freezes, expands, makes the crack deeper, and that process just continues and wreaks havoc on our roads. That makes sense? Okay. So this is what most materials do when they freeze. They contract. Like this is, I think, glycerin. It froze that, and like it gets smaller rather than bigger. Okay. So this is kind of cool. So as you cool water down, it does contract a little bit. Okay. But until it reaches 4 degrees Celsius. 4 degrees Celsius is the most dense that water gets. After 4 degrees Celsius, you cool it down, and it actually starts to increase its volume and decrease its density. Okay, with that, as it sets up to start freezing. Okay. So the consequence to this is pretty cool. All right, so water in a lake, typically during the summertime, the hotter water is going to be on top, the colder water is going to be below. That's what we'd expect. That's not earth shattering. If you've ever swam in a lake and like dove in deep, it gets cold fast. Right? It's like, whoa, okay, that's what we'd expect. Okay. But in the wintertime, because 4 degrees is the most dense, it actually sinks on the underneath the colder water. This is not normal. Does that make sense? Like the colder water is less dense than the 4 degrees. Okay. Cool with that. So fish are going to chill out near the bottom. So if you ever go ice fishing, that's something to be aware of. Now, this also has some pretty cool implications. So when a pond freezes, so as it cools down, it's gonna drop back down like this this turns into like cools off fall winter. This heat's gonna leave this, and as it gets colder, it's gonna sink down, which we would expect. But in order for water to freeze, this whole body of water first needs to become 4 degrees Celsius. That's one of the reasons why it takes ponds and lakes so long to freeze, because the whole amount of water needs to drop to 4 degrees Celsius. Once it's at 4 degrees Celsius, then this whole thing is uniformly dense, and then heat continues to leave, and this colder water stays on top. It floats, and as that happens, then at some point that turns to ice. Okay, but that ice naturally, because it's less dense, floats on this water, which provides a layer of insulation for this water below. So it doesn't, the ponds don't readily freeze solid. The longer or colder the winter is, the thicker this ice is going to be as heat leaves this, causing this layer to freeze. But so long as you don't have like a super crazy long winter or super cold, there's always going to be some water here that fish can survive. Good with that? Okay. So you can regurgitate the facts that I just gave you. There we go, 4 degrees Celsius. And where is that located? At the bottom. Good job paying attention. Good with that? Okay. Now, what would happen if that wasn't the case? Well, a couple things. One, if water contracted when it froze, this would become more dense than water, and so ice would sink, displacing some of this water, like pushing it up. So as things froze, and it would expose this water to the cold air, so this process would happen faster. Sink, expose, sink, expose. At some point, we're just like raising the fish up, and the fish swims in shallower and shallower water until it's like not very conducive for pond life. Go to that. The other thing that would happen would be like polar ice caps would sink, and we probably wouldn't have beachfront property, but we'd definitely be close to the ocean. Go with that. And that is, I think, all I have for you today.